mass of the why does it come slow? You can change the mass of the chassis. You can change the mass of the to the extent possible of the plate element, and certainly you can change the spring constants of the gasket and of the flexible grommet. And because and these results show you what you can possibly do. So the conclusion was, in a situation where no rebouncing of the cabinet takes place, the dynamic response depends for the given drop height on the ratio of the mass of the chassis to the mass of the plate element, the ratio of the spring constant of the outer and the inner cushions, and the geometry and the material of the plate element. In order to make the stopping brake distance and the maximum acceleration sufficiently small, one should design a dynamically stable system. That's a system whose vibrations are remote enough from the resonant conditions. It is advisable that the plate is made as thick as possible for the given mass. This will lead to a low weight, high natural frequency of its elastic vibrations, and large flexural rigidity of the plate element. This element should be fixed in its gasket in such a way that its actual support conditions are as close to the clamped conditions as possible. The interesting thing about this example is in my entire course, I addressed a system with a single degree of freedom. I even tried to reduce to a system with a single degree of freedom elastic systems, which are by the very essence are systems with many degrees of freedom. But in some cases, you not only cannot do that, you don't want to do it. And this was a situation when you can achieve a dramatic improvement in the protection of a portable devices if you put it of the type of box in a box. And but also, in this case, if you don't do it the right way, it can result in more harm than good. And you can end up with resonance conditions that will kill the device. So you should do an analysis, you should do modeling before you build the real thing. Let's now consider I call it again, the conservative Duffinger oscillator with the application to shock protection of portable devices. So far, we considered with this nonlinear system, it was only a system with a rigid characteristic of nonlinearity. Why we did that? Because that was the physics of a situation when we had reactive forces. But generally speaking, if this is the relationship between the force and, let's say, displacement. In a linear system, certainly we have something like that. In a nonlinear system, the system that we were examining for several hours, it looks like this. So the system becomes stiffer and stiffer when the displacement increases. But there are also systems with a soft, this is rigid characteristic, this is a soft characteristic of the restoring force. And the soft characteristic is, for instance, you have a typical soft characteristic of the restoring force for a ship in her roll. So in this case, at a certain significant angles of the heel, the restoring forces go down. So that's nonlinear characteristic of this type. Another example from structural analysis, if you have a wire, and we will discuss that later in application to portable devices, that buckles. And I want to remind you that buckling is when it's a loss of elastic stability. Any beam, or a plate, if it's subjected to compression, and let's take a beam like this. When it is subjected to compression, certainly here we generate a similar force. And if this force is high enough, this beam will buckle. And you probably heard this, the force at buckling is called either Euler force or critical force. And for a beam that you see here, this force can be calculated by a very simple formula. So this is pi, and this is EI is called flexural rigidity. For a, you remember for a plate it was like this, but for a beam it's like this. It's Young's modulus of the material, and I is the moment of inertia of the cross-section, and L is its length. And this is the Euler force. So if you have a situation when a beam buckles, let's say this is a beam that buckled, and then after you keep it's a beam, let's say apply the force, and the beam buckled, and then when you continue pushing it, it results in a situation when it becomes a nonlinear system with a soft characteristic of nonlinearity. And this is probably good in some cases, and let's see whether we can benefit somehow from that. What you see here is, again, you see here this drifting equation, but in this case we will consider two cases. It could be with a plus, but it could be also in front of the mu, it could be a minus. If it's a minus, it's soft characteristic. It's a plus, it's rigid characteristic. And you can see here that these are two types of behaviors, and with the soft characteristic, it behaves, of course, if it's linear, it's the same point at the middle, but in soft characteristics it behaves the way that what you see here on the left side, the upper line, and the rigid characteristic, the lower line. But also, I already mentioned to you a couple of times, we want also to see how the product of the factors that are responsible for the displacement and the acceleration, how the product behaves. Because we want to minimize the product, and to us it's probably a good rule of thumb that if the product is lower, maybe we have the better system. Or later on we'll examine the situation, will be the load divided by this product. In this case, the product is lower, this characteristic go up, and we will call it a quality. But this is the line in the middle, and the line in the middle actually is a product of these two characteristics for systems with the soft characteristic and with the rigid characteristic. Let's take a look how these, let's assume that we have all the power in the world and we can design an ideal shock absorber. What it actually means? This means, of course, in actual portable devices, we cannot do what people do when they bring down space shuttles. They bring down space shuttles, they turn on the jet engine, and therefore, so they can have a reasonably small, low braking distance, and everything works out fine. But we don't have a jet engine, so we can do it only in a passive fashion. And maybe we can find a material, like a material that will act as a cushion, but this cushion will act, hopefully, supposedly, ideally, as this jet engine acts. What that means, that let's say that we deal with a device that is able to withstand a certain level of acceleration, which is A. So what it means that we want to have such a cushion, such a material, such a structure, that at the moment when this device hits the bottom, the acceleration will be exactly A, and then when it will, at the last moment, when the velocity is 0, the acceleration will be also A. So in other words, we want to create, to ask ourselves, what kind of a cushion, what kind of a resistance we want to have so that the A always will be the same. Whatever the device can withstand, let's do that, but not exceed the A. And if we'll do that, we'll end up with a formula that you see here upstairs. That means it should be a material whose viscosity or such that the displacement, the speed of the portable device when we drop it should be a square root of 2gh minus ax as a function of t. In other words, this formula shows a relationship between the velocity at a certain point of time versus displacement at this point of time. If such material can be created, we are in a good shape. But let's also think, let's assume that we can create such a material. What will be gain, what we would be able to possibly gain if, by a factor of what, compared to a situation when we don't have such a material. So the quality, we can introduce a parameter where you see here in the denominator is 2gh. That means the initial velocity squared, and there's nothing you can do about it. And in the denominator, it's a product of the maximum deceleration and maximum displacement. In other words, the maximum braking unit. And since the maximum deceleration has a minus, we put a minus in front of this fraction so that to obtain a positive level of quality. And it could be shown that the maximum that you can get here in an ideally nonlinear system, whatever you can do, is equal to 2. So it's something. It certainly should be a smart material that provides a nonlinear cushion of the device to be protected. Let's now take a look whether we can bring in nanowires that will buckle this way, and how high will the quality here in a situation when we have an array of nanowires. Actually, nanowires can be grown in many ways. For instance, you can use plasma CVD, you can use thermal CVD, so you can always have a substrate and you can grow nanowires on one side or on both sides, it's fine, and then you can use this structural element as a cushion, and that's what you see here. And we described in detail that in the chapter in this book, which is Dynamic Response of Micro and Optoelectronic Systems to Shocks and Vibrations, and it has the part which is called extension. That's why I described there. And you see here, this is how this quality could be obtained and calculated for the given maximum displacement, maximum acceleration, and for this particular system, how these displacements, accelerations could be obtained. And this is in a linear system. I want to emphasize that in a linear system, the maximum displacement is a square root of 2gh divided by frequency. And the maximum acceleration is the same frequency times the square root of 2gh. Their product will be independent on the frequency, and that means independent of the system. That means there is nothing you can do to improve the situation in a linear system. And its factor, this factor of quality, will always be 1. But in a nonlinear system, in a highly nonlinear system, it can be made as high as 2. It's something. Indeed, such system should be characterized by a constant acceleration that is turned on at the moment of the beginning of the braking, is then turned off at the moment when the velocity of the mass to be protected becomes equal to 0. Then the corresponding braking distance can be found, determined as what this formula says. For this equation, we find that Q is equal to 2. The quality of a nonlinear system can be, as evident from this formula, considerably higher than 1. For the maximum force value approaching the critical force, that's situation buckling, the system quality can be almost twice as high as the quality of a linear system that's will not be very far remote from the ideal situation. So that's an interesting result, because typically we say nonlinearity is not our friend, it's our enemy. Maybe it's too a strong word, but it's something situation that we want at least to understand, maybe to fight against. But here is the situation when we want to bring in nonlinearity as a soft cushion. In a situation we'll be using soft protective devices. So I'm saying that a simple calculation procedure, predictive model, has been developed for the evaluation of the evaluation of the shock protection capabilities of a wire array. An appreciable gain in quality can be achieved in comparisons with linear springs cushions by employing wire elements subjected to compression and operated in the pre-buckling and post-buckling conditions, but close to buckling modes. Again, why we need close to buckling? Because certainly with a very soft cushion, we want to avoid a situation when it's become so soft that you'll have a blunt impact, and that's certainly not desirable. The design with a flexible wire or a wire array as a shock protective means should be carried out in such a way that the wires perform as close to buckling conditions as possible, preferably in the pre-buckling mode. And a couple of words about photonic systems. Here you see that's free vibrations of a fused bi-conical taper light wave coupler. Just one example. I published many papers on that, but for this course, I don't think that I already mentioned that the students, the listeners, the users of this course are very much interested in photonic systems. But this is a very interesting structure when you have a combination of, it's a non-prismatic beam, number 1, clamped, number 2, and in addition to that, the material is a very funny animal, where when it is its Young's modulus increases when it's subjected to tension and decreases when it's subjected to compression. And therefore, when it vibrates, certainly this manifests itself. And that's why I'm saying here both non-prismaticity and non-linear stress-strain relationship should be accounted for when evaluating the frequency of the free vibrations of the fused bi-conical taper light wave coupler. And some results are published in the Journal of Solid and Structures and Journal of Light Wave Technology. I will skip these particular results, And I will thank you for surviving my course. And the symbol here, again, I put the quality at the end, and it will be a product of the velocity at the impact squared and divided by product of the maximum acceleration and maximum displacement, or maximum deceleration with a minus. And for a single degree of freedom system, we can obtain a nonlinear system. We can have an improvement as high as 2, but even a greater improvement we can obtain in situation when we'll use like a box in a box, when we will make the situation richer in terms of the degrees of freedom. I didn't try to evaluate that, but I would guess that we can obtain a significant improvement of the existing cushions if we will if we'll go in 2 directions simultaneously. We'll bring in nonlinearities with soft characteristics of the restoring force, and at the same time we will design a shock protective system with more than 2 even degrees of freedom. Thank you very much for your attention, for surviving my long, short course. Thank you.